Hello AP Chemistry and welcome to 14.7 Catalysis. So, a catalyst, first of all, is something that is present at the beginning of the reaction and is basically produced again during the course of the reaction, right? So it is consumed and then produced again such that it remains unchanged at the end of the reaction, right? So if we look here, right, in terms of catalyst, right, we have some bromide ion. That bromide ion comes out the exact same at the end, which means that bromide ion would be our catalyst in this case. Okay? And if we look here at this graph, this is a great depiction of what it means to have a catalyst, right? We say that a catalyst lowers our activation energy by providing an alternate mechanism, okay? An alternate mechanism for the reaction to occur, right? And again, right, if we look here, right, so it's kind of like saying we went from one step to having an intermediate produced, right? So a second step, a two-step process, right? Which lowers the overall activation energy, making it easier to go from reactant to products, okay? Because again, activation energy via the Arrhenius equation correlates to the rate of my reaction, right? Well, it correlates to K, which then correlates to my rate, right? If I decrease my EA, I decrease my K, which increases the rate of my reaction. Yes? What did I just say? If I decrease my EA, I increase my K, which increases my rate. That's definitely what I mean. I'm not 100% sure that's what came out of my mouth the first time. Okay, types of catalysts. We have our homogeneous catalysis, right? Wherein every body is in the same phase, right? Meaning we have aqueous solution, right? Aqueous ions in my aqueous solution, and we produce our aqueous ions at the end, right? You'll note that it's not actually clear at the end, right? And that is because bromine does have some solubility, right? And so some of it is going to stay in there, right? That's why the solution has a little bit of color to it, more so than when we originally began. But this is basically what we did in the lab when we did our potato and peroxide, right? In that we have a catalyst, right? In that case, it was catalase, right? Which basically expedites the process of hydrogen peroxide to form my oxygen. Okay. Heterogeneous catalysis, right? Like the word implies, right? Meaning that we have different phases, right? Most often, that means we have a solid state catalyst and usually gaseous, though it could be aqueous, reactants, right? And all this serves for us, right, is the metal, it's often a metal, right, serves as an adsorbent, right, a place where my molecules can adsorb, and that sort of facilitates the breaking of the bonds, right, or it facilitates the orientation aspect, but it basically, again, lowers our activation energy so that we can increase our rate constant and increase our overall rate, okay? So the reactant components adsorb, right? And then they react and then they desorb, right? Not to be confused with absorb, because if you write absorb, right, it's going to get marked wrong because that's not what's happening, right? It's not going sucked to the inside, right? And note here, right, it's always going to happen at the surface, right? Because if we think about, for example, metals, right, we understand that in a metal, right, every atom is bonded to all of its neighboring atoms, which are bonded to all of its neighboring atoms, so forth and so on, right? And what makes this top layer of metal atoms different? Right. It is not bonded to nearly as many atoms, right? Which is why these surface metal atoms actually have a little bit more reactivity than the ones on the inside, okay? Which is why all we're getting is adsorption to the top, the layer of atoms that is slightly more reactive, right? And that's where the reaction is occurring. That's where we're getting our catalysis to occur. What else was I going to say here? I don't know. I can't remember. That's good. All right, biological catalysis. So you talk a lot about this in freshman biology, I think, and maybe a little bit in middle school, right? But we have giant proteins in our body that act as enzymes, right? So when we hear the word enzyme, we should think protein, right? Where a protein is just, right, a long string of amino acids that have been bound together, and folded appropriately, right? So here, long, giant string, right, composed of thousands of atoms, right, that gets folded into a very particular three-dimensional structure, right, such that there is an active site, okay, or a place where its substrate is meant to bind, right? Make sure you know those words, right? We have our enzyme with an active site where our substrate is meant to bind. So the substrate is the thing that is being acted upon, okay? And so then what happens in this lock and key model, right, which is not actually how we believe catalysis occurs, right? So if we look here, this is a very specific shape, right? This is a model now, right? Where our substrate literally fits that shape, okay? My substrate bonds, let's not say bond, our substrate interacts with the enzyme forming a complex, right? And how is it that they attach to one another? Right, via IMFs, right? Which is basically how all of this folding happens anyway, right? So what happens is that this substrate and this enzyme, right, in this active site have to have some kind of shared IMF, right? There is an IMF and a shape that fits this substrate and usually this substrate only, right? And it fits inside of there. Then this part catalyzes a reaction such that we can produce different products. Note that these products cannot have the same affinity for this active site, right? If they do, right, if these products have a strong affinity for the active site, they aren't going to leave, right? Does that make sense? Right? So the substrate has to have a stronger affinity than the products, otherwise the products won't leave, which is actually how certain inhibitors work, right? Like when you hear about certain drugs that are called inhibitors, one of the ways that they work is that they model the substrate, right? So they look and act like the substrate for a particular enzyme, but instead of being released, right, it binds so tightly that it just stays stuck, right? It doesn't do the same thing, and which means that this enzyme is now out of commission, right? Until that substrate loses its activity in whatever way that happens, right? And note this is a lock and key model. We also have the induced fit model, which is the preferred model, like what we actually assume happens, right? Wherein you see that there's this active site, right? And we have our substrate that would go in there, but it doesn't fit so much like a puzzle, right? As it's sort of like a baseball glove where it kind of fits in there, right? But once it folds around it, it does fit just right, right? And that this active site shape would change a little bit, right, as the substrate approaches it. Okay, same idea though, right? They bond via some kind of shared intermolecular force, right? Which kind of goes back to that EP where you saw that little string of a protein, right? And what we can do is, depending on the amino acids there, right, we can make it be so there's lots of hydrogen bonding opportunities, for example, or lots of LDF opportunities, right? Whatever it is, that's going to attract our substrate in there. Anyway, and then the same thing happens, right? And we would have our product released. Yeah? So do be mindful, three basic types of catalysts, right? We have our heterogeneous and homogeneous catalysts. And this, though, biological catalysts, they're kind of like their own separate category. Okay, that's all for now. Thank you for listening. Be good, and I will see you soon. Bye.